I told you that there are three main topics in calculus: limits, which we got our introduction to last chapter, derivatives, and integrals. Well, we spend the rest of the semester really diving into this world of derivatives, and we get our introduction today, and then we will not hit integrals until second semester. So it takes us a long time to learn how to take derivatives and then learn how to use them, and that's really where we are going with this. So this is our introduction, but the introduction is going to look really familiar. You guys have actually seen this formula already before. This is the definition, and it's actually back from chapter 2 of the derivative of f at a particular point. One thing I want to point out is it does, again, specify this is the slope of the line tangent to the curve. So if they asked you to find the slope of the line, or remembering that that's what a derivative is, the slope of the line that is tangent to the curve at a point A is the limit as h approaches 0 of f of a plus h minus f of a over h. That formula should look very familiar to you because we had that last chapter. We just used it to find an instantaneous velocity or an instantaneous speed. You remember that phrase and that formula? It's the same thing. They are the same thing. Okay? So if you remember what that was, we were making h become 0 because we were looking at the slope. That's where this whole formula was derived. The slope between 2 points, and we just made those 2 points have a distance between them essentially becoming 0, h being the distance between our 2 points. And as that distance became 0, we found the slope of the line tangent to our curve at a particular point. And we're going to see this now for a third time in just a second. And it is incredibly important, this formula. You have to know this one inside and out, the limit as h approaches 0 of that whole thing that came from our slope formula. So does anyone still need this page? You're going to see again that same formula on this page, and it is the definition, and I'm going to add to this the formal definition of a derivative. And it says this: the derivative of a function with respect to x, and that's not going to mean much to us until way later on when we start taking derivatives with respect to another letter. And so as we take a derivative with respect to x, it's going to look like this. Here's an introduction to a notation for a derivative, and it's this little tick mark up here, and we call that prime. F prime can look like that. You see it again right here, F prime. And we see again our function. Now the only difference you see here compared to what we saw on the last page is this has an x in it, and the last page has an a. Guys, x and a are going to become pretty much interchangeable. They can either stay our variable, or they can be the specific number that we are plugging in on that particular place. But what you need to know is this formula. And I think almost every AP exam that we've run across, you'll have a straight up question that asks you about this formal definition of a derivative, and being able to recognize the function that is within that formal definition of a derivative is going to show up over and over. Okay, so making sure that we know this formula. All right. So moving forward, how do we then use this to find the derivative of a function? Just a second, we'll let people get that down. All right, anyone still need this page? Okay. Before you get going too much on this one, I am going to break this down a little bit. It's still got that definition of a derivative up in the corner here, so that's what we just saw on the last page. Here's our definition of a derivative. It just kind of reminds you of the formula we're going to use. And the function on this first example is this: let f of x equal x squared plus 2x. And it asks us to do this. Now look at the question. Find the slope of the tangent line. That's a way of asking to find the derivative. So they could directly just use the word derivative. They could ask you to find the instantaneous velocity. They could ask you to find the slope of the tangent line. It's all asking you to do the same process, and that is to use our definition of a derivative. And you notice that it asks us to do this 4 times for one function, right? Now I'm not going to do this 4 times, and so basically it's kind of how is the question being asked. When they're asking us to do the slope of the tangent line, they're asking us to do the derivative at that particular value. We are going to actually do a generic derivative where I don't plug in a specific number. We're just going to let it be a variable a, until the very end. So because they're asking me to do this 4 different times, I don't want to go through what you're going to see on this page 4 different times. I'm not going to plug in any of those individual numbers until the very, very end. I'm going to do a generic limit at x equals a. Okay, so how do we do that? What we do is we're going to set up our limit here. And when we do this, it'll always be set up the same way. You will have your function that we will write the first time, plugging in a plus h everywhere there was an x. So that would be here and here. And then I will subtract, and I will do the function a second time. And the second time, we only plug in a. So this one, for whatever reason, it takes a little bit of getting used to. But every time you set up this formal definition of a derivative, you are going to write out your function 2 full times with a subtraction between the 2 of them. And do substitution 2 full times. The first time what I am subbing in is a plus h. So where my x is where I put in an a plus h. The second time I only sub in a. Question so far. The next several lines are just the cleanup process. So this is where my algebra skills are going to kick in. How can I clean this up? Because ultimately I'm trying to take the limit of this thing. Well, I cannot take the limit of it as h approaches 0 right now. Because if I were to try direct substitution, it would be subbing in a 0 in the bottom of this fraction. So this is where my cleanup process is going to happen. Okay, so now we're going to clean all this up. Okay, so working on that first one, I've got a binomial squared, which means I've got to write it twice in FOIL, right? If I write that twice in FOIL, I would get a squared plus 2ah plus h squared. Distribute that 2 through here, plus 2a plus 2h. And then this is where you got to be careful with your algebra. On the next one, it is subtracting this. So I'm going to have to distribute that negative through. And I would get minus a squared minus 2a. Still good? Okay. Clean that up even more. What you're going to notice is some things are going to end up simplifying here. I've got an a squared minus an a squared. Okay, well, those would just cancel each other, right? A squared minus a squared. I've also got a 2a minus a 2a. Those are going to cancel each other. Okay. And what I have left, 2ah plus h squared plus 2h. You notice all of those, I said the letter h, right? 2ah, h squared, 2h. All of those have a GCF of h. And that's kind of where we're headed with this, is I'm trying to simplify this down so I can eventually plug in 0 for h. And in order to do that, I've got to simplify. We'll pull out that GCF in the top. If I pull an h out of each of my terms that are left over, we would have 2a plus h plus 2. That's where the simplifying happens, is I can simplify the h out of the top and the bottom. Leaving me with 2a plus h plus 2. And now I don't have a problem with my direct substitution. Now remember what we are directly subbing into. H is what's approaching 0. I have an h right here. That's where I direct sub in, right? So I would have 2a plus 0 plus 2, which would be 2a plus 2. What we just found is a generic derivative. Okay? Your generic derivative, and this is not a rule, but most often is still going to have a variable in it. Okay? And so now what I can do is I can take that generic derivative back to our question, which was this. Find the slope at 0, 2, 4, and negative 3, and use that generic derivative to do that specifically at each of those x values. So the generic derivative we got to was 2a, what was it, plus 2? Okay, so that's our derivative. And now I'm going to evaluate that, and this is actually a good time to talk about this. I have mixed letters up there, x's and a's. Again, don't get hung up on the x's and a's. That is going to be where you plug in your numbers, wherever it says x or wherever it says a. So I would evaluate this at 0. Two times 0 is 0, plus 2 is 2. So the tangent of the slope of the tangent line at 0 is 2. Plug in 2. 2 times 2 is 4, plus 2 is 6. Slope at 2 is 6. Plug in 4. 2 times 4 is 8, plus 2 is 10. And plug in negative 3. 2 times negative 3 is negative 6, plus 2 is negative 4. So looking at the problem we just did, guys, it did take me a little bit of algebra, right? I had a little bit of algebra work to do to clean up that limit. Right now, there's no way around that, is we're going to have to spend a little bit of time. But if you notice, because they were asking me 4 questions about the same function, I chose to do the generic derivative, meaning I left the letter a in there. I had a derivative at the end that had the letter a in it, and then I could just replace a with each of the different numbers they asked me to evaluate for. The other option is that I do that for each one individually, and I would have had that much algebra work for all 4 of these, which is why I don't want to do that. If you see on this next one, they are only asking me about 1, we can plug it in at the beginning instead of waiting to the end. You can always wait to the end, it doesn't matter. But if they're only asking me about one specific x or a value, I actually can plug it in at the beginning and work with numbers then instead of variables. Okay? And I would probably only take this route if I was only evaluating for one number, and we are only evaluating for one number on this particular problem. So let's do this one more time. Our function is x cubed this time. They remind us what the formal definition of the derivative is, the limit as f of a plus h minus f of a over h as h approaches 0. And this time we are doing this at a equals negative 2. And guys, they will, again, interchange the letters a and x in these formulas. So again, that's just the number that we are going to evaluate this at. And the number shows up right here. Wherever there's an a is going to be the number that we are plugging in, whether it says x equals or a equals the number at the end here. So your option is you can actually plug in the number at the beginning of the derivative process instead of at the end. So let's look at one where we do that. So our function is x cubed. Remember, as I set this up, I'm going to do my function twice with a subtraction between the two of them. So as I do the function the first time, our function is x cubed, and I'm supposed to plug in my number plus h into x cubed where there is an x. So that would be negative 2 plus h cubed. I do that again. Here's my function a second time. My function is only one thing, cubed. And on the second time, I just plug in the number. Okay. Clean all of this up. And again, we're going to clean it up to the point where I'm able to directly sub in. And that's not until I get rid of the h in the bottom of my fraction. And again, let's talk some algebra here. Remember that if I have a binomial cube, that means I'm writing it out 3 times, right? And then negative 2 cubed is negative 8. If you have something like this, my suggestion is that you FOIL 2 of them and then we'll distribute the third. I would do it in 2 separate steps so we don't get confused as to what we've done here. FOIL this, I would get, let's see, 4 minus 4h plus h squared. Minus a negative is plus. And then we were going to distribute. So I distribute the negative 2, and then I distribute the h, which is going to give me 6 new terms as I do that. Negative 2 times 4 is negative 8. Negative 2 times negative 4h would be 8h. Negative 2 times h squared would be negative 2h squared. And then I do the same thing with h. h times 4, h times negative 4h would be negative 4h squared. H times h squared would be h cubed. Okay, and we start cleaning it up and combining my like terms. Negative 8 plus 8 is gone. And then I've got some like terms to put together here. 8h and 4h would give me 12h. Negative 2 and negative 4 would give me negative 6h squared. We can take out a GCF of h. Which lets me cross off the h's so I can do my direct substitution. Okay. When I do my direct substitution, again, I'm plugging this in for h's, and I'm plugging in 0. So this is what's left over, I can plug in everywhere I saw an h, a 0. And you can see I get 12 plus 0 plus 0, which is 12. That is specifically our derivative at x equals negative 2. So now at the end, I don't have to plug in negative 2 because I did it at the beginning. So basically showing you side by side two problems, same process, one where we plugged in the number at the top, one where we plugged in the number at the bottom. Questions on finding the derivative of a function? Okay. Does anyone still need this page? Okay, let's talk about the derivative of a constant. If our function is a constant function, meaning just a number, no variables, right? So on this one you can see we've got f of x equals 5. As I look at putting that into our formal definition of a derivative, if I follow the rules, it says that I write this out, I evaluate my function for a plus h, and then I evaluate my function for a, which means wherever I have a variable, I'm plugging in a plus h, and I'm plugging in a. As I go back to my function, as I go to try to plug in a plus h, it's just 5, right? There is no variable in a constant function. So the first time I write out that function, it's just 5. I've plugged in a plus h everywhere there was a variable. There are no variables, right? And then I subtract, and then I plug in a wherever there's a variable. Well, again, this is the second time I write out that function. There is no variable, right? So I am evaluating for a plus h, and for a, it still just looks like 5 because it's a constant function. So look what happens as I clean this up a little bit. 5 minus 5 is 0. 0 over anything, doesn't matter what it is 0. And I can evaluate this as h approaches 0. It's going to be 0, right? So we see that the derivative of a constant is going to be 0. Does it matter what the constant is? No, and not at all. If my constant was 20, it would still say 20 minus 20. That's still going to be 0, which is going to simplify down to 0. It doesn't matter what I directly sub into that. It's still the number 0, right? And so what we're seeing is the derivative of a constant is always 0, and we just proved it. We used the formal definition to prove that. Any questions on that? All right. The last little thing you're going to see here is what's called your alternate definition of a derivative. In the alternate definition, I would say on this, put it in your notes. You don't need to spend any time memorizing this. You do need to memorize the formal definition that we had at the beginning, which we've now seen 3 different times in our notes. The alternate definition, if they ever wanted you to use this, they would put it in the question for you. Use the alternate definition to find the slope of the tangent line at whatever. Okay, and they would list out the formula for the alternate definition. And all it's doing is this. Notice we don't have an addition in here, right? It says f of x minus f of a over x minus a. And this time, x is what is approaching a being a number. Okay, so x being a variable in this one, a being a number in this one, if we were to have a number to approach. So let's go ahead and do one example where we evaluate something using our alternate definition. This one I did not give you a number to go towards, but we could change the problem at the end here and actually go towards a number if we wanted to do that. So it says use the alternate definition to find the derivative of f of x equaling the square root of x. So our alternate definition says the limit as x approaches a. We evaluate the function for x, which would just be the square root of x, minus evaluate the function for a, which would be the square root of a, over x minus a. I wouldn't be able to do direct substitution on this one right now, because if I tried to sub in a, which is what x is supposed to be approaching, right? If I tried to sub that in where there are x's, I would end up with a minus a in the denominator, right? Now, back in a couple weeks ago, we talked about how do I fix something like that if I can't do direct substitution and I've got those radicals in the top. You remember that part? And we used our conjugate to fix that. We would do the same thing here, is I would use my conjugate to fix that. When I multiply by my conjugate, remember we are going to get first thing squared minus the second thing squared. Well, the first thing squared is x minus the second thing squared would be a. I would just let those sit next to each other in the bottom here. And that's where I'm going to be able to simplify that out. X minus a in the top and bottom is gone. And now I am able to do direct substitution because it's not going to give me a 0 in the bottom of my fraction anymore. So as x is approaching a, I can plug in a wherever there was an x. And knowing my good algebra, those are like terms. Square root of a plus square root of a is 2 square roots of a, right? So I would say 1 over 2 square root of a. Again, if they had asked me to do this as a equals some number, I can then at this point plug in that number and say my answer would be 1 over 2 square root of 5. Or at this point I could have put in the 5, and the 5 would have been here, here, and here. As x approaches 5, and I would have the square root of x minus the square root of 5 over x minus 5. Okay? And you would just replace all the a's with whatever number you are supposed to be approaching in that problem. Any questions on your alternate definition? Okay. Part of the challenge in calculus is figuring out what are they asking or what is the notation meaning. And derivatives is no different than that, because there are several different ways we can denote a derivative. Up to this point, we have looked at prime. And I just want to give you a couple other ways that this can look. So it can look like f prime, which is what we saw on the very first page with our formal definition, or y prime if it happens to be written as y equals. It can look like this, dy dx, and that's how it's read, dy dx, or it's also read the derivative of y with respect to x. If your function was called f instead of y, you would say df dx, the derivative of f with respect to x. Or they can move that to the side, d dx of f of x. And again, you could replace that with y. It could be d over dx with a y here instead of an f of x. So f of x and y are always interchangeable. And that's just all different ways that they can note to ask you to do a derivative or to indicate a derivative. All right, when you are done with this, we are actually going to start our assignment together. So if you will find wherever you are going to do your assignment today, we are going to get that started together as I give people some time to write that down. I will come back to this. If you are still working on writing this down, I will come back to this page after we get our assignment started. Okay, so your assignment is on page 105. You guys are doing 1 through 12. Now, here's the deal, guys. If you show up tomorrow with a list of answers, if you go back to my notes, do you see how much work it took me to do a derivative? Okay. Now, I feel like we could have skipped maybe 1 or 2 of those steps if you're a little bit more efficient with your algebra, but you're not skipping all of them. Okay, so you need to make sure that you are showing me, at minimum, setup is always a point on derivative questions. Setup, a line of work, and answer, if not multiple lines of work as you are doing this, okay? So we're going to start problem number 1 together. This is exactly what it looks like in your book. Go ahead and find wherever you're doing your assignment. I'm going to